Hello again, folks. Today we're going to be covering section 6.5 and 6.6. Here is a quick view of the calendar to confirm. This video is for Thursday, June 9th. So I'll be covering section 6.5 and 6.6. And these are about properties and solving equations that involve exponential and logarithmic expressions. Okay, now the packet that I have for you today consists of these pages. This is a sort of strategy for the first section, 6.5. You're more or less simplifying things, but you know it's debatable about what is more simplified, to have something in the condensed form or in an expanded form. Sometimes it's better for you in this scenario or in this scenario. So if you're given something that is condensed, what can you do with it? If it's just an expression, you could expand it. If something is given to you expanded, then you could condense it. You could abbreviate it more or less. Let me add one little note here. When you are doing performing the process of condensing, this would be an appropriate order, right? Applying what will be called the power rule, the product rule, and the quotient rule, pretty much in that order. You'll be doing this as well when you're expanding, potentially. But I think the order is a little less strict, all right? It's really this order when you're condensing that is important: power, product, quotient, okay? Another thing to remember is some prime numbers: 2, 3, 5, 7, 11, 13. You can't memorize them all, of course, but it would be good to know those by heart. Here is an overview, basically, of properties, okay? The things that I was just referring to are here: the power rule, the product rule, and the quotient rule. I'll be using those probably mostly. These other things are useful, all right? Converting situations where you have one, right? Where you have the argument is the same as the base. And the inverses. You remember when we first discussed functions that if you have true inverses, when there's a composite of a function and its inverse, the outcome should be x. All right? There's a similar effect when you're dealing with logs and exponential expressions. Okay, and then there's the change of base formula down here, which is also useful. When we get into solving equations, these two will be very useful. One-to-one relationships. If two functions, two expressions have the same base, they're both logs such and such, then you could just pay attention to the arguments, basically. And a similar effect to when you have exponential expressions. If they have the same base, then you could just pay attention to the exponents. Okay. This is an old diagram I drew just years ago. Just to remind you of what it means to be prime in comparison to what is composite, say, or the number 0 or 1. It's good to know primes by heart, at least if you're the first few of them. Then this is an overview strategy for section 6.6. This will be the solving techniques, depending upon what is given to you. Yeah. And lastly, you might have, well, this is another older diagram. You might have this already. These are the rules of exponents. The power rule for exponents is useful, as is, you know, this what happens when you have a negative. And this is another old diagram, U-Substitution. I tried to bring this up, I think it was in chapter 2. It's very useful now. So I'll give you an example with that. Okay. If you're following along, do print this out and I'll discuss it in more detail. Okay, put this aside. Alright, I may have to adjust the lights. And I'll pull up my projection. Oh. Reasonable, I think. Okay, so firstly, since we're covering section 6.5, and this is incorporated in section 6.6, the properties of logarithms. Think of it as basically you are simplifying logarithmic expressions. So again, it's debatable what is truly simplified, whether it's in the expanded form where you can see every little part. It's sometimes makes things more clear that way, or in the condensed form where something is more succinct. All right, it is less complicated looking in a condensed form. Anyhow, if you are tasked with expanding something, you'll be given something that is condensed, and you'll be trying properties. You'll be basically trying to factor arguments. All right, so you're paying attention to what should be in a parentheses as if it was in function notation, right? And you want to factor something down to prime numbers. All right, now that's why I put this here just for reference. So if you have a number like 15, you would want to factor it down to 3 and 5 at some point. Okay, because those are prime numbers. All right, and that will expand something. If you have something that is already expanded and you would like to sort of toggle the thought and condense it instead, right? What you want to do is try to combine the arguments into one argument, right? Just beware, you can only do this if you have logarithms that are the same base, right? Do not attempt to do that when they're different bases, right? In that event, as I was mentioning earlier, in reference to this, do this first, this second, and then this third, all right? You'll probably be applying the power rule, the product rule, the quotient rule when you're performing this task, all right? But I think you have a little bit more leeway in this case, all right, when you're trying to expand something. When you're condensing, this is what is probably the proper course of action. Okay, power first, product second, quotient third. All right, now, what am I really talking about? These list of properties. So let me pull this up here. Okay, this is the whole kit and caboodle. And again, the ones that are immediately useful are this one, power rule, all right, the product rule, and the quotient rule. Don't throw away these other things; they're very useful as well. All right, but this is what I was just talking about. Here are the models, just to zoom in on them, that you want to think about when you're condensing. Okay. This is very handy. Okay, I might just do that. Do myself a little favor and grab my markers. Okay. I'm considering the power rule. What is being referred to here is the exponent of what is in the argument. All right. If it is conducive to the problem, you could essentially legally put that exponent out in front as a sort of coefficient. Okay. If something is given to you that way, then you can think about it backwards. All right. This is the difference between expanding and condensing. You know. As for the product rule, all right, these are really easy to remember. All right. If you have a product, all right, you have two things that are being multiplied in the argument. All right. So if it suits you, you could separate them as two terms, separated by a plus, as if they were two things being added, all right? And similarly, in consideration of the quotient rule, if you have two things that are in the fraction or ratio style, they're divided essentially, so you can write them as two terms separated by a minus, all right? All the other features would be the same, The argument on top is the same before and after. The bases are the same before and after. Right. Okay. When we get into solving equations, you more want to take advantage of the one-to-one property and the inverses. Right. This is probably a little bit more important in section 6.6, right? As are the one-to-one properties. Okay. Let me just clear that out. Anything else real quick? Okay. think that's fine. Okay. Let's do some examples. I'm going to turn off my projector now. All right, just have that maybe handy as a reference. Okay. And I'll try to go through this with you and refer to those features as necessary. That wasn't too wise. So I'm going to try to confine myself so I don't have to keep erasing. Split the board here in two. A better black marker than that one. That was kind of lousy. Okay. So we'll work on expanding. All right, suppose you had to expand, that is the instruction, log base 3 of the argument 30x times 3x plus 4. All right. If you, again, just kind of keep, if you're not familiar with this at all, keep the reference, because it's pretty much anything that you would need to use at the ready. Just as we go through that. Okay, now what happens here is you have essentially two things, because they're butted up against one another, serving as a product. Right? In the argument, remember things encapsulated in parentheses are an argument. All right, so something times something else. All right, and ideally, if we're going to expand this, we want to break everything down as far as we can, including to prime numbers where it is applicable. All right, this is going to be a usage of the product rule, which says that when you have a product, however complicated it is, you could separate it into a sum. All right, so this would firstly be the log of base 3 of 30x plus the log of base 3 of 3x plus 4. All right, and you might be content with that, but you actually can break it down a little bit further. All right, this sum 3x plus 4, you kind of stuck with that, but this is still a product. All right, so as long as this is a product, and it would be understood as being 30 times x if they're pressed together like that, you could go a step further. All right, you could say that this is the log base 3 of 30 plus the log base 3 of x plus this that's left over. Okay. And if you analyze the number 30, you may realize that that is a composite number, so you could factor that even further still. Think about when you were in maybe middle school and they had you have, draw factor trees. You break this down into something times something makes 30, just not 1 because it's not a prime number. You could start with 3 and 10, you could start with 5 and 6, but eventually you want to break it down into all primes, and in that event it would be 5 and 2 and 3, which means the end result should be this: the log of base 3 of 5, all right, plus the log base 3 of 3, plus the log base 3 of 2, and then the x that was there, log base 3 of x, okay, and then these guts over here carried down, plus log base 3 of 3x plus 4. Now if it was just 3x by itself, you would continue and separate that 3 and the x away from each other as a sum, but because they're part of essentially a binomial, this plus 4, you're pretty much stuck with it. All right, so just leave it like that. All right, this would be the completely expanded form of the original thing. Okay, there's a little bit too much glare, right? might help. Not that level. Not that. Nope. Okay. What's my living room? Is that visible? What the hell is balance of light and darkness? I think that's okay, right? Log 3, log 5, log 3, log 2, log x, log 3x plus 4. All right. Here's another. Suppose you had to expand the log, that should be a common log, 2x over 3. All right, remember, if there's no base given, you would assume that it is a common log, which means it would be base 10, but you don't even have to worry about that. You're just going to write the word log instead of any 10s anywhere. You don't have to do that. All right. This would be a usage of the quotient rule, all right, which says that if you have a quotient, something divided by something else, all right, then you could make it, instead of a sum, as in the case of multiplication, you would make it a difference. So it would be the log of the top thing, so 2x, all right, minus the log of the bottom thing, all right? Now, it just so happens that when you get that far, you notice that there is a product left over because you have a coefficient and a variable. So these two things being what they are pressed together, you could break them down according to the product rule now. So this much would be additionally the log of 2 plus the log of x minus the log of 3 that was down there. Okay. And that would be the end. Expanded form of this expression. Okay. All right. Let's do some uglier ones. Let's say that you have this. You want to expand the expression natural log, so ln, all right? And inside you see a radical x squared, and this is 3 here. So the natural log, which would make it a base e, you don't ever have to write that. It's understood, right, when you have a natural log, all right, of the argument that is a cube root x squared, all right? Now in this case, what you're going to do is, again, toggle in your mind that you could write something that is a radical alternatively in rational notation. All right? If it's in radical notation, that's as it's given to you here, you could write it in rational notation. And in that respect, you take into consider what the index is and what the exponent is here. All right? The index is essentially equal to a denominator. All right? So, rewritten, right, you would have the natural log of x to the 2 over 3. That's the index, always is a denominator, and whatever the exponent is coincidentally here, that's the numerator. Now, this is an example of the usage of the power rule. All right, the power rule for logarithms as opposed to the power rule for exponents. Okay, and all that you can do with this then is take this and make it a coefficient. So an expanded version might be 2/3 times the natural log of x. Right. And you that's fine to leave it like that. Okay. One more, and then we'll shift gears and deal with the condensed versions of these. Okay. I may need more space, so let me erase this because I'm probably going to have to use that anyway. I have to open it back later. Here is kind of the kitchen sink thrown at you. The natural log of this multi-layered problem. So you have on the top, the square root appears to be with contents x minus 1 times 2x plus 1 squared. And then underneath it, x squared minus 9. This is, you may recognize right off the bat, something that can be factored. Further, this is the difference of two squares, it's just that 9 is more or less disguised. And so that would be a binomial, x minus 3 and x plus 3. But you could do that now, or you could do it later. If you just want to get in comfortable with the logarithmic properties, then I would say you can worry about it after the fact. All right. Let's try to straighten out the top here. All right. If this is, again, something in radical notation, top has radical notation, all right, you can, if you want to, convert this to rational notation. All right. It is, in this case, although it's not written, an index of 2 because it's a square root apparently, which means you can eventually change that into something on top that is raised to the exponent of 1/2. All right. All right. Let me hold off on doing that just for presentation purposes for a moment. That's eventually going to occur, just like this. The bottom is eventually going to factor more. Factor the difference of two squares. Okay. Maybe the most obvious thing about this is that this is a ratio because this has a line here. So maybe start with that. All right. And in that case, what you have is the natural log of the top, x minus 1, 2x squared plus 1 squared, minus, according to the quotient rule, the natural log of the bottom, x squared minus 9. This is according to the quotient rule. Okay. I should encapsulate that, sorry. Right. Now at this point you pretty much have no choice. Let's take this radical and rewrite it in rational notation. So what that would mean is that the natural log of the square root would be, I'm going to use a bracket just to, because there's so many parentheses here. Encapsulate all of this into the 1/2, right? Why? Because this is an exponent of 2, right? And since this has two pieces and one of them has a an exponent of 2 here, just not to confuse anything, I'm taking just the radical by itself and keeping it outside of this bracket I've written. Right? The guts are still the same inside here. You still have this x minus 1 and this 2x plus 1 that is being squared. Okay. Now, the power rule, right, would immediately say you could take this exponent that is outside here and park it in the front as basically a coefficient. So I'll take advantage of that and I'll put 1/2 out in the front. Right? That would be 1/2 times the guts that you see here. Okay. Now, these are still two things, complicated though they may be, butted up against one another, so they're a product, right, without the dot. So what I could do at that point is apply the product rule to this, right? Just not forgetting that there is a half that would in theory be affecting both of these things. So that half is still there, right? And I'm going to change the color as I apply this product rule just for the sake of presentation. I'm going to put a bracket here and then put the sum inside this bracket. All right. You could take brackets away at will, you know, and put them wherever you feel that they're necessary. Natural log, all right, of the first chunk, x minus 1, all right. According to the product rule, when two things are multiplied, even if they're ugly, you could break them into a sum that has the same type of logarithm. So a natural log would be base e. And then you have this, 2x plus 1, that's still being squared by itself. Meanwhile, this is still hanging on here. Right. So you have off to the right side here, the natural log of x squared minus 9. Right. This is still over here on the far left, that's the right side, and here's the left. Something that you could whittle down further. I'm out of space, so I'm gonna just kind of like erase a little bit and then continue. Okay, continuing with this logic. The inside guts here would be another example of the power rule, right? So if I applied the power rule just to this thing as it has an exponent here, that would put a 2 here, all right? I would like to do that first because what I'm going to do eventually is try to get rid of these brackets and try to simplify whatever I can. In that event, I'm going to distribute the outside coefficient of 1/2 times both of these things, and you'll see the effect on each of them. All right. In the first case, it's going to continue to be 1/2 up in the front times the natural log of the guts x minus 1. But when you take the half and then you apply it to this thing that had the power rule applied to it sort of intermittently, it's a half times 2, which induces a cancellation effect. And therefore, you're just left with the natural log and the guts 2x plus 1. So, plus 1. That much is done. Okay. The junk over here, right, I'm now going to do the instruction I left for myself, which is that I really should factor the difference of two squares a little bit further. It is a good thing in the long run to commit to memory, memorize some things like that, the model that would be the difference of two squares, and know that 9 is really just 3 squared disguised, right? Which means that the factored incarnation of this would be x plus 3 and x minus 3. That's the way those always work out, right? Once you figure out what the bases are, that's how they would be. A binomial, almost identical except for the signs, right? But that leaves you with another product, which means, and you do have to be careful, there's a minus here. All right, so when you're breaking up the logarithm that is comprised of these two factors, x plus 3 and x minus 3, you would really do yourself a favor if, again, you threw in a bracket as a reminder, or parentheses, that this negative would have to be distributed. So I'm going to just take the factored form here and apply what would be the product rule again, applying to those binomials, which would give me the natural log of x plus 3 plus the natural log of x minus 3 encapsulated entirely. Okay? And now, having done that, distribute this negative to each of these, right? Which means the end result would be a half times the natural log of x minus 1 plus the natural log of 2x plus 1 minus the natural log of x plus 3 minus the natural log of x minus 3. And remember, in the case of these binomials, because they are a binomial, essentially, they have a term x and 1 and 2x and 1, you can't go any further with the factoring. If this was just 2x, then you would break it into a natural log of 2 plus the natural log of x. But because it's binomial, leave it alone. Same situations here and here. Okay? And that's the whole thing. Expand it. All right, now we go the other way. Condensing. Incidentally, if you're wondering why they're going through all this trouble, when you get to solving exponential or logarithmic equations, it is sometimes to your advantage to do either of these things first, especially the condensing. All right, you're going to be using properties, but you may change something, that the appearance of something first is what I'm getting at. Okay, so suppose you're going to condense now. Log of base 3, 5, plus log base 3, 8, minus log base 3, 2. All right. The thing you have to remember is you do products before quotient rule, okay? And before either of those, the power rule, if you can help it. All right. The other thing you have to remember is do not attempt to combine different base logs. All right. If they're not the same base, they have to be autonomous pieces. All right. So in this case, it's just intuitive, all right, because we read from left to right. Your focus would be here. They're both base 3, so they can be recombined. And in that case, they would be log base 3. Now, instead of as a sum, two things being multiplied, 5 times 8, which would make this log base 3 of 40. And now, this other stuff that is sitting here, the subtracted portion of the show here, they can be recombined, the quotient rule in reverse, more or less. So, the focus now is on these two things as the quotient 40 over 2, which if you can simplify it, if you have actual nice, warm, fuzzy, and familiar numbers like 40 and 2, means that in the simplest incarnation of this, it's just log base 3 of 20. Okay? Another one of these. Take a sip of water here. Okay. Here's an ugly one. Suppose you had to condense 2 times log of x, and that's a base 10, which again you don't have to worry about. It's understood. 4 times the log of the binomial x plus 5, and then you have a coefficient of 1 over x, yippee, right, times log of 3x plus 5. Okay. So we're going to apply the power rule first, the product rule second, and the quotient rule third. All right, it's a good habit. All right. There are some things that have powers. All right. This coefficient, and even that coefficient are powers in theory. So according to the power rule, more or less in reverse, all right, we could take this 2 and write it there, all right, and this 4 and write it there. And I'm just taking the coefficient, not the sign, leave that there. And then this, which is in the rational style. There is one thing you have to remember too. When you have something that is in rational style, right, you could put it in, that is in this case 1 over x. You could readjust it to make it look more like just the standard exponent, right, which would be a negative exponent, right? So if this is a denominator, that would make this a plus 1 as an exponent down here. Adjusted would be a negative 1x, right? And since it's still a coefficient, even in this form, all right, you could just plop it over there, so minus x. Okay, according to the power rule for logarithms, all right? Which means you have this, just to make it a little bit more clean, log of x squared. You can put this inside, it's not going to hurt it. All right, log of x plus 4 to the 4th. In the case of a binomial, I would have to put it like that. Yeah, for the sake of consistency, because I can't stand myself, I put 2 there. It doesn't have to be. Plus log of 3x plus 5 minus x, because of the adjustment and the power rule. All right. Okay. Now, all right, my intuition would have been, well, you work left to right, all right, and addition and subtraction according to the standard rules are that these are equal operations, right? But they're logarithms, so it's a little bit more complicated than ordinary numbers, they seem to be. So instead, apply the product rule before the quotient rule, right? Which means that, and perhaps a little bit weirdly, your focus is going to be here. All right. So, all right, in that event, this, according to the product rule, because it's a sum, all right, would have these things tied together according to the same log. They're both the same bases, like this: x plus 4, 5 to the 4th times, all right, this is the product, 3x plus 5 to the negative x. Okay. All right. Now, meanwhile, this is still floating around here. So log of x to the square, minus that. Now, because there's all that is left, is this this difference. What you're going to do is apply the quotient rule now. All right, which means, all right, you're going to get log, they're the same type, with x squared above the line. All right. Below it will be this first factor, x plus 5 to the 4th. And then adjacent to it would be the second factor, 3x plus 5 to the negative x, closed. Okay. All right. turn my projector back on. And I'm going to discuss the other handout here that is an overview. Okay, these are some techniques for section 6.6. In this case, you're solving equations that may involve exponential or logarithmic expressions. Right? There's sort of a divide here. All right, let me adjust the lighting in here a little bit. And talk about some of the features here. Okay, I tried to summarize. It looks a little blurry, so let me just see if I can get the camera a little bit sharper here. That's not improving it. All right. Okay. If you have a problem, first start with deciding, do you have things that are exponential equations or logarithmic? All right. There is a cool alternative to doing the calculation, which is to graph stuff, right? I mentioned this maybe a while back in chapter 2, when you're trying to graph, when you're trying to solve quadratic equations, you could attempt to graph something and then look for the x-intercepts. This is similar to that, except that each side of the equation, whatever is given to you, you're going to plug them into your calculator as the first y equals and then as the second y equals. And then you're going to look for point of intersection. Right? Because the point of intersection would in theory be the common solution, like a system of equations would be. Now, if they don't cross, then there's no solution. All right? No cross, no solution. Okay? And that you can get your calculator to do for you. All right. The things that you really should do via calculation are, when you're given the same bases, then you could apply what is known as the one-to-one property. Essentially, what the one-to-one property is telling you is that if you know up front that these two bases are the same, then just pay attention to what would be the exponents only and make those the equation. All right. If you have a situation where you're not given something that has matching bases, do attempt to try to translate into a common base. So if you're given different bases, it might be possible to translate something so that they do look the same, and then you can apply the one-to-one property, right? The one-to-one property, again, is on the sheet, right? Here at the bottom, look at this in the exponential example here. When the bases are the same, then all that you really have to pay attention to are the exponents. In a similar way, when you have equal logs on opposite sides of equals, then you just pay attention to the arguments. Okay? Sometimes you have to manipulate. If they give you something that doesn't quite match, but it is adaptable, try to. All right? In some situations, when this fails, what you can do is apply a logarithm to both sides. It's kind of like multiplying by it's not multiplication itself, but it's similar to multiplying the entire equation by some convenient number when you're trying to eliminate denominators. In this case, you're applying the same expression, a logarithm, to both sides. All right, what I would do is use base 10, i.e. the common log. All right, if 10 is already involved somehow, because there'll be a cancellation effect. All right, if not, just stick with the natural log. All right. That is the situation when there is no base 10. All right. Now, if you're given a base e, for sure you want to use natural log. Why? Because they're inverses of one another. All right, and there's a sort of a cancellation effect. The natural log of e is just 1. All right. okay? Or, right, you could try factoring. What I'm alluding to here, remember when you're factoring is factoring and then using the zero product rule. You might try U-Substitution in a situation like this. Well, I'll give you an example of that. All right. Now, if you're given logarithmic equations, again, you could try the graphing technique. Right? Plug in the left side as y equals and the right side as y equals, and hope, that they cross, because the point of intersection would be the solution again. All right. If you have more or less the normal situation where you're given log of x equals a number, all right, then again you're going to attempt to translate this into exponential equations, which was the technique that you had employed in section 6.3, right? So technique from 6.3. All right, and then apply, inverse properties. All right, if it's possible. Sometimes it's not. All right. Now, if again you're given the same logs, that means that they're the same bases. So the one-to-one property would also be true. In that event, you're not paying attention to the exponents per se. You're paying attention to the arguments instead. Right, the contents of the parentheses. All right. The good news is, there's a method for everything. So you might feel a little sketchy, but as you do these, you get more and more comfortable. All right. I would, as we go through the examples, maybe keep this page handy as a reference. All right, and we'll do a bunch together. All right, I'm going to start with the graphic one, just to show you. Let me turn this off. Again, I'm going to start out with trying to spare myself from to erase. I'm going to cut this in half. Work into a smaller and smaller space. Soon I will be teaching from the trunk of my car. There you go. Great. Solve. We'll try this one via graphing technique. You don't have to do something this way, but it's cool, all right? This would be an example where you're given 3x plus 1 equals -2. Okay, this is an exponential equation, right? Why do I say that? Because there's evidently a variable in the exponent. Right? So you would try maybe to adapt it so that you have the same bases, but the bases are 3 here and -2, so you're up the river without a paddle. Is that the expression? All right. You really can't adapt this. So what you would try is to graph it, and what's going to happen is you'll see that something weird happens. We'll pretend that basically this half of it is y equals 3 to the x plus 1. All right? And then the second half of this, even easier, would be y equals -2. All right? Here are some expectations, right? If you just have y equals a number, whether it's negative or positive, all right, this is a horizontal line. Right? Remember, horizontal line equations are dumbed down. They're not y equals mx plus b. That would be a diagonal line. They're even simpler than that. They're just a whole number, a constant, right? Just a number, I should say. But in this case, it is a constant. All right, -2 whole integer. All right. Anyhow, on a graph, and these would be superimposed upon one another, you would for sure have a horizontal line running through y equals -2, right? Which means the intercept, if you were curious, would be 0, -2. Okay? Now, this is an exponential function. So, a couple of things. It's going to have this shape, right? We would expect that, right? It might be a little bit tinkered with. It might, in some cases, if there are more features to the transformation, it might be flatter, a little bit steeper, perhaps. But just do what's easy, right? I'm trying to do it brute force, or you could use a calculator. I'll get to that in a second. If you put 0 in place of x, which would imply y-intercept, right? Then you're just going to have 3 to the first, which is just 3, which means that this dot here, right, where it goes through the graph, would have to be 0, comma 3, right, regardless, all right? Now, without even using your calculator, all right, you could make a prediction about, do they cross, right? That can't possibly, because under normal circumstances, right, exponentials have a horizontal asymptote, right? And this is the horizontal asymptote, right? Y equals 0. Meanwhile, the second part of this is beneath the asymptote. If it was a positive 2, then yeah, they'd cross at some point. But they don't cross at all. So there's no solution in common, all right? Because they don't cross, all right? You could rule that out altogether, all right? For those situations, and you'll see later in the, when we do the logarithmic equations, I have another graphing one. All right, you'll see that they do cross, right? In that event, it would be very handy to have your calculator, because it could specify, right, for you. All right, so that's kind of cool, all right? All right, now if you have an example like this, 2x to the minus 1 is equal to 2x minus 4, all right? You would notice, or you're training yourself to notice that, these have the same bases. They're exponential equations for sure, because we'll look what the variable is, all right? And they have the same bases. Since they have the same bases, all right, have this handy. What's a good technique for doing that, all right? Well, if they're the same bases already, all right, you could take advantage of the one-to-one property, which again means you really just need to pay attention to what the exponents are. Now, they're more complicated than just a number. They're algebraic expressions, but who cares, all right? You could do that till hat, all right? Here's the one-to-one property for the exponential type, right? Whatever is sitting in the exponent on the left, set it equal to whatever is in the exponent on the right. Right. So we're really just focusing up here, all right? X minus 1, we're going to set equal to 2x minus 4, all right? It's a linear equation, all right? Degree 1, whatever you want to call it, all right? So make a little table, rearrange the parts algebraically. I like to have letters on the left, so I'm going to take this 2, acknowledge that it's a positive, and subtract it from both sides. Cancellation effect. And then on the same line, just to save some space, a little bit of time, I'm going to take the constant and put it over here. So plus 1, plus 1. All right, cancellation effect. So what do we have? You end up with, because this is a positive 1 here, 1 of each sign, you subtract them, you do get a negative 1. All right, and then over here, subtract them, you'd have a negative 3. All right, but it stands to reason that if negative x is equal to negative 3, that positive x would be equal to positive 3, right? The minutia would be that, well, I'm going to move the obvious coefficient from here to here via opposite operations, which would be dividing by negative 1. Both sides to balance, these would become positive. It's just 1, which you don't have to write. It's superfluous, all right? And the outcome would be positive 3. All right, here's an example of where you're not given something that has the same bases up front, but maybe you can adapt it. So suppose you had 8 to the x plus 2 is equal to 16 to the x plus 1, right? Now, not to make too much of a speech or put too fine a point on it, but, all right, if anybody in your life has ever said to you, I don't memorize stuff, forget that they ever said that, this is bad advice. All right, because if you have your multiplication tables memorized, then you might recognize that there's a relationship between these things. All right, and if you know anything about, powers of 2, all right, which is really just glorified multiplication, you go, both of these, I could adapt them. So you're not going to be content with the way things are handed to you. You're going to change them in a legal way, as long as it's consistent. All right. So in the case of, just paying attention to the bases here for a second. If I were going to make this 2 to something, right, because I recognize that 2 can be, the product of 2's will be 8 at some point, and take this 16 and do the same thing, all right, then what was here, x plus 2 and x plus 1 will be multiplied by whatever that figure is there. All right, why multiply? Because, just to remind you, from a long time ago, all right, the power rule of exponents, which is another piece of paper here. All right. The power rule of exponents is when you more or less have an exponent raised to an exponent. And in that case, the abbreviation would be the product of these two things. So in my example in my paper, 3 times 2, that would be 6. This is different than the product rule for exponents, which is when the bases match and you just add the powers, the exponents. Okay? So we have to figure out what the exponent would be here to make 8. We have to figure out what the exponent would be here to make 16. All right? 2 times 2 is 4. 4 times another 2 is 8. So this would be a 3 here. All right? And then if you were to do 8 times 2 and another 2, another iteration would be the appropriate word. This would be 4. Right? Now the bases match, and just like that, the one-to-one property, right, says that if the bases match, you really just need to pay attention to the exponents, right? So what I have here is 3 times x plus 2 on one side and 4 times x plus 1 on the opposite side. I do have to simplify it a little bit, but it's going to be a linear equation, a linear expression set equal to a linear expression. So distribute 3, distribute 4, all right? This is 3x plus 6 is equal to 4x plus 4. And at that point, you have a little table that you make. All right. Again, my preference is to put the variable over here. So opposite of positive is minus 4x. Take the whole thing, subtract it. Move the 6, subtract 6. Cancellation effect. Positive 3 minus 4 would be negative 1 again. X. And one of each is subtract, you get a negative 2 on the other side. Right? Again, this is the result, positive 2. Right? If negative x equals negative 2, then positive x is what you're done, would be positive 2. The minutia would be dividing by negative 1 both sides. Right? Divide by negative 1, divide by negative 1, you get a positive. Right? That's pretty cool, right? All right, moving on. Here's a situation where you really can't change the base. Well, you can actually in this case. What am I saying? They're just uglier. All right. So if you have 2 to the 5x is equal to a radical. All right. All right. Remember, radical notation could be changed to rational notation. All right. In which case you have something that is an exponent. All right. Do that first. It may not be obvious that that is in fact the same base as this, but if this is really an index of 2 and that's a 1, and again, people never bother to put those figures there and there in the case of the square root, that is just degree 1, all right, base. But I put them in personally because it makes it easier for me when I'm trying to adapt it to rational notation. Remember, the index is the denominator. So since it's a square root, it would be a 2. All right. That means that this is, once again, 1-to-1. So you just have to pay attention to the exponents. 5x is equal to a half. If you're going to isolate x, you're going to perform the opposite operation of multiplication, which is speed racer out there. Divide by 5. And then you would divide by 5 here, which means that it's going to be on the bottom with that. Okay? Therefore, x is equal to 1/10. Moving along here. Let me erase this because I'm going to need a lot of space probably. Here's an example of when you would apply a logarithm to both sides of an equation. So look at what you have first. This is 5x plus 2, and this is on the opposite side 4x. Right? Now, again, go through the motions. You could graph them, and they would cross in this case probably. All right, but it's probably a little bit easier, especially if you're doing this by hand, to pull the technique that I'm going to show you. All right, you can't change these to a common base because it's just not going to happen, right? At least not in some easy fashion. All right, so what you're going to try is the technique of applying a log to both sides. All right, just to point at it. Sorry. All right. So, if you're given different bases, and again, you would try to convert to a common base first. All right. It didn't work. It won't work in this situation. All right. Then what you're going to do is apply a logarithm to both sides. Again, remember, you can get away with murder in math world as long as you're consistent. Whatever you do to the left side of equals, do to the right side. All right. In this, in that event, I would say, well, if there is a 10 as a base here or there, then implement common log because it is itself a base, and therefore there'd be an inverse somewhere. But if there isn't a 10, just go with natural log, all right, which would be base e. All right. So, as long as you're consistent, if you take the natural log of this side, all right, and the natural log of this side, right? Now you can apply rules of logarithms to them, right? For example, the power rule, right? Right? The power rule, firstly, would say whatever the exponent would be here, it's a binomial, you could make that a coefficient. So then you would have x plus 2 sitting out in front of natural log of 5, right, on the left side. And a similar effect over here on the right side. So x times the natural log of 4. All right. Now, it's written behind the binomial, and normally when you're doing distributing, you think of things as, something sitting up in the front. It's still a binomial times something, right? I regarded it as a coefficient, but you could, really, if you wanted to, you could reverse the situation. The bottom line is that you're going to distribute, all right, this to each of these contents now, since there's 2 of them anyway, which means that this is x times the natural log of 5, right, plus 2 times the natural log of 5. Meanwhile, on the opposite side, look what you have here. You have the natural log of 4. And in the process, don't get bogged down and forget that what are you trying to figure out? We're solving equations, so we want to know what x is. So in that event, if we need to, all right, we could start algebraically shifting things around where it might be more convenient, all right? Say, for example, the thing that has the x in it and the thing that has the x in it, it might be to our advantage to have adjacent to one another, not on opposite sides. All right. So here's what I would do. All right. Move the thing that doesn't have x it's really just a number. It's just an ugly number, it would be a decimal, over here, all right? Move the thing that has an x, like this x, natural log of 4, over here where its buddy is, all right? You want the x's isolated generally to one side, and you want numbers without letters on the opposite side. It's just unusual because you have a natural log here. Don't get scared, all right? This is a positive, so I'm going to subtract it. Ugly and complicated though it may be, whatever it is, it's something minus itself, so it goes away. All right, and I'm going to park it over here next to its buddy. All right, as close to a like term as we possibly can have. If this thing, 2 natural log of 5, is taking a hike over there, then if it's a positive here, then it would have to be a negative on the opposite side. And again, I don't know what the decimal is off the top of my head, but it's something minus itself, so it would cancel. And just for the sake of space, I'm going to park it over here. Okay, so to write it a little bit nicer, a little bit neater, all right, the things with the x's involved, x natural log of 5 would be on the very far left. This minus x natural log of 4 would be just adjacent to it on the right side of it, and they equals, and then this minus 2 natural log of 5. Okay, now, if these things are being multiplied by x each, and they would have to be since they're, you know, coefficients of x, then I could factor them. All right? So, for the lack of space, what I'm going to do is rewrite that in a factored form. All right, so the factored form of this, factored out x, would be x in front, right, the common factor, a monomial, and then a parentheses of the junk that you rip x away from. So in the first part of it, in here, it'd be a natural log of 5, and then a minus, a natural log of 4, right, and then on the opposite side, again, still negative 2 times natural log of 5. So, couple of things I can do, all right. I'm going to take advantage of the power rule here, where if I have a coefficient, negative or not, up in front of a logarithm, all right, instead of having it written there, I could make it the exponent. All right, which means that this half of it would be the natural log of 5 to the negative 2. Right? Right. What happens when you have a negative exponent? Right? It doesn't make the value negative, it makes a fraction, basically. This is an abbreviation, more or less, for a fraction. So this is really the equivalent of 1 over 5 squared, right? Which means that this is really the natural log of 1/25th, right? Weird as that may seem. Right, it's a regular number, right? Nonetheless. Okay, now as for this stuff here, since it's in factored form, it is x times this gobbledygook. Even gobbledygook can be moved again. I know that drives people crazy. All right, back and forth, but somehow that's the way it unfolds. All right, you could move this chunk, however complicated it is, over to the opposite side for the sake of isolating the x. So if I'm to multiply, because they're factors, I'm going to divide this by 5, natural log 4, all right, and scoot it on over. Right? All right. It might be better to put this in quotient form first, all right? But it will work either way, right? It's just sometimes a little bit harder to read it after the fact. So, leave it alone. All right, it'll work either way. Something ugly minus it's divided by itself cancels. It just goes to 1. All right, that leaves you with x, the thing you're looking for. And on the opposite side, this chunk in red here, natural log of 5 minus natural log of 4. Okay. Now that quotient, all right, pardon me, this difference, according to the quotient rule, can be combined. All right. Quotient rule says when you have a difference of the same base, then you can mash them together, condense them, right? So that you have this 1/25, just to make it nice and neat, over the natural log of 5 over 4. Okay. Now, that is correct, and you can leave it alone, all right? Since this is a decimal number and that's a decimal number, and they're both, probably irrational, I would be not surprised. You can enter that into your calculator and see what the result would be. Or, if you want, all right, just to remind you of something, there's the good old change of base formula, right? And the change of base formula is normally written to get to this point. But what if you wanted to put it as one nice, neat logarithm, all right? And I would want to do that. Take a look at this, all right? Normally, we start with something that's a non-base 10, so not a common log, or non-base e, not a natural log. And we have something else, some unique base, some unique argument. And we want to write it in this style because, at least in the old days, we could have entered that into our calculator because before the software was updated, all right? But in this event, it would be kind of cool to take it backward that way because then you have something that's just one logarithm rather than a division of logarithms, all right? So let me remind you of something. And this is, unnecessary, but I think it's kind of neat, all right? If, and I like the more recent model I typed yesterday. If the change of base formula looks like this, that the logarithm of base, whatever it is, whatever unique base, and whatever unique argument can be expressed as this quotient, all right? The log of whatever you like, different of a on top, and the log of same base, whatever it is, on the bottom. And usually, again, if you were doing this with your calculator, you just have common log A over common log B. Then if you start with something in theory, that is a natural log, that means it's log of E, all right? Nobody bothers to write this, but I mean, it really is log of E and log of E, all right? Same, all right? Then what we can do, if this is the A value and this is the B value, is put those things here and here respectively, and then you just have one log. All right, to me that's more condensed than anything, right? So that's kind of neat. 1/25 and a weirdo base of 5/4. Right? So this means that ultimately x is equal to, I'll just put it back in natural log style rather than log base e, or log of that. Right? No, I have to in this case because it's a different base. Log of 5/4 base, argument 1/25. That's kind of cool, right? Again, the software can handle dealing with something like that, all right, or something like this, fine, nowadays, all right, but historically, it wasn't the case. So here's what you would do, all right? If you want to get a decimal number, all right, you have two options at least, right? You can hit second and then alpha and then hit function 2 And one of the options in the menu, assuming that the software is up to date, would be log base, right? And then you have 5, right? Then you can intuitively put in the weirdo base of 5/4, all right, and the argument of 1/25. I, again, can't help myself. I like to do things intuitively, so I'm going to hit Math, scroll over to Num, go down the list, and see if I can put it in the intuitive way. So Enter, and there, it adjusted it, so that's cool. So 5/4, and then the same thing essentially, because I'm being a twit. 1/25. 25, right? I'll look at it that way. Good. Okay. And all goes according to plan. You get the correct decimal, right? Negative 14 and change. Okay, 4251, whatever you want to round it to. Okay, if you just did it the more fastidious, is that the word, expeditious way, you might at this point just type natural log of 1 divided by 25. All right, divided by, again, natural log, and then put 5/4 / for the division, and then close the parentheses, be a good person. And you get the same figure, negative 14 and change, right? All right, that's cool. All right. As is often the case in math, there's more than one way to do something. And I would say do ultimately whatever you feel most comfortable doing, but never give that up, and realize that, and keep it in the back of your head, you have options. Right? That's empowering, right? To realize that you have options. Freedom of choice, right? It's very American. Right? All right, moving on. All right, here's a different type of problem where you have 100 on one side and 20 times e to the 2, and there's a different variable, t, instead. Okay, that's a t, I swear, script t. All right, so what's the actual variable that you're solving for? The exponent, therefore it's an exponential equation. Yeah, the e would give it away too. And you have some tinkering to do with it first. In general, you want to isolate e to one side or the other. All right, so we're going to get rid of the coefficients up front, all right, or at least reduce them. If this is being multiplied by 20, then divide by 20 here to cancel, and divide by 20 here to balance and to simplify. And you would have 5 is equal to e to the 2 to the t. All right, now in this case, let me point out it on my sheet. When you're given e as a base, all right, and it's isolated, you're going to pull the trick basically of applying a logarithm, but you're going to opt for, given a base e, applying the natural log, all right? What happens when you apply the natural log is that they are inverses, so there is more or less a cancellation effect, right? You just got to be consistent and do it to both sides. Remember, you can't get away with anything unless you're very consistent. So if you take the natural log of e, you must take the natural log of 5 at the same time. I hope you will forgive me. I just like the variables being on the left. So I'm going to write it like this instead. And it's not really performing algebra, it's just being dweebish. All right, so a couple of things. The power rule simultaneously would say that this could be written up in front, all right? Meanwhile, these are inverses. All right, so there's something of the cancellation effect. Essentially, you're left with 1, all right? Now here's a reference again to the properties. All right. Where to put that? here's the inverse properties 1 and 2, all right? If you have a function and its inverse composite, one inside the other, as you have in this case, they normally would produce the x, all right? But the function is 2t here instead of an x, all right? That's the only difference, all right? This is just by itself 1, all right? All right, so kind of burn that into your brain if you don't really want to dwell upon the fine details too much, that's what it is. Now, if you feel a little sketchy about that and you're not satisfied, all right, remember, you could always prove that this is the case. If you have the natural log of e, all right, then that would be this, really, just rewritten, the natural log of base e to the e, all right? What happens when you have, up here, you look at conversion here, the log of a base and then the argument is the same figure, it's 1, all right? Essentially what's happening here. All right? You could, if you want to, all right, take it even further. You can say, remember from section 6.3, right? When you're trying to convert an expression from logarithmic form into exponential form, you kind of disguise it to look like an equation, and you do so by saying, all right, well, this is equal to some letter, so let's just say x, all right? And then you draw the jelly bean, you know, all right? In which case, e to the x would be equal to the argument, that happens to be this e here, all right? And if there's no number there, one would assume it is 1, all right? And therefore, according to these being the same bases, what would x have to be? 1, regardless, all right? Anyhow, I would do this just as a favor to myself. If you don't want to dwell upon the minutiae every single time, just remember, if you see the natural log of e, they're inverses, all right? And there's essentially, in the context of equations, more or less a cancellation effect, so it's just 1. And if there's a variable here, then it's just this, 2t, all right, because it would be that times 1, all right? Over here, you kind of stuck with this, all right? But then you just manipulate by dividing by 2, and then t is equal to whatever the natural log of 5 divided by 2 is, all right? Which is probably a very long decimal figure, right? Just curious at this point. The natural log of 5 divided by 2 should be something like 0.8 and change. All right. Okay. Yeah. Okay. Moving on. Space. I think it might be time to clean this eraser later. Okay, so next one. This looks more or less like an equation just from the onset, right? But we're going to solve it just for the simple instruction. 4e to the 2x, all right, plus 5 is equal to 12. Okay. Now again, when you're given things like e as a base, you want to isolate them and then apply the natural log, right? Again, for the reason of there's something like a cancellation effect. So manipulate it to isolate e. Move 5 by subtraction. All right, that leaves you with 4e, 2x is equal to 7. And then there's the coefficient of 4. So I'll divide by 4 here, and you get a crummy improper fraction, but it's legal. All right, and then you have this. E to the 2x is equal to 7/4. All right, now once again, apply the inverse to it. Right? And since this is a function with in its inverse, one embedded in the other composite, there's going to be a cancellation effect. Right? Do it to both sides to make it legal. that will be a regular some decimal number. The power rule simultaneously would have the effect of putting this up in the front, right? So this is going to be equal to 1, right? And then 1 times the coefficient of 2x is just 2x again, right? And then on the opposite side you have this, 7 over 4, divide by 2, and you have that again. The natural log of whatever 7 over 4 is divided in half. Okay. This problem that you're going to see is a reminder on two fronts. It's going to record, I would do this with U-Substitution, but also, I mean, I haven't mentioned it in a while, you should check for extraneous solutions which arise from maybe squaring something, or if you're multiplying or dividing by a variable. An extraneous solution in a nutshell is a dud, all right? It isn't your fault, it's just something that happens from really extreme measures. Anyhow, it's algebraically correct and the arithmetic would be fine, but when you check it, it doesn't work with the original equation. So we're gonna be leery of that, all right? Let's see. Suppose, in this case, you have two e's. So you have e to the 2x, and then you have minus e to the x. And this is equal to 56 over here. All right, a couple of notes. You can't isolate, really, e in this case. At least not yet. All right. So, given certain conditions, this might be a good candidate for U-Substitution as a technique. And I included that here just to pull this out. It's something that I had with the forethought, the foresight, sort of broached in chapter 2. All right. Here, just as a reference, I'm going to include it in this packet. All right. All right. Basically, U-Substitution is when you just don't want to get bogged down with details. All right. You have to meet certain conditions to really make this work. You essentially want something to look like a trinomial to begin with, and you have all the parts. All right. But you want a polynomial set equal to 0. So start with that, all right? If you manipulate this so as to scoot this over to here, right? If it's a positive on this side, it would logically be a negative on this side. And then you have e to the 2x minus e to the x minus 56 equals 0, all right? So a trinomial, esque looking thing, all right, because it's not really a polynomial per se, but it has 3 terms and it's set equal to 0. All right, you're basically making it look like a polynomial by using u's instead. All right, now let's check some other things. All right, you want all of the exponents to have the same base. All right, so this is a base e and this is a base e, so good. All right. Then you want the third term to be a constant. Well, lo and behold, it's a 56, so that's also good. All right, now the last thing is, the degree of the first term should be double the degree of the second term. All right? This is x, so maybe it's a little hard to read it that way, but what is this? Just twice as much. So it's double that, all right? So we're meeting all the conditions of U-Substitution. What you're gonna do now is zero in on the middle thing, all right? And just disguise it. You're going to say, instead of having ex, I'm just going to call this u, all right? And then I'm going to interpret this similar thing of, something of similar persuasion here to the squared version of that. So if you'd like, you could say to yourself, well, that much of it, the e to the x portion of this is just u again, but it happens to be squared. So there's a 2 hanging on, all right? And now you have something that is probably many times easier to factor, all right? Why? Because it simulates a trinomial, a genuine polynomial, and usually what happens is when you're trying to factor it, it's a binomial sitting next to a binomial. So something squared up in the front here and here. And then the factors of 56 that would be convenient would be 8 and 7, right? And if you want them to multiply to make a negative, they have to be one of each sign, right? Meaning one thing positive and one thing negative. And if you want simultaneously for them to subtract and reduce to a 1, that is a negative 1, the larger magnitude has to be the negative. Right? And then you have that. Now, you can take advantage of the zero product rule, right, which says, again, it's subscribing a word to something you know intuitively. 0 times anything is 0, so even something ugly. All right. In this case, you have a factor, 0 plus 7, that might be equal to 0. And in this instance, you have 0 minus 8 might be 0. All right. At some point, it doesn't have to happen yet, you're going to have to reverse the substitution because we don't really have u, we have just u standing in place of something uglier. All right. But the best part of this is that we can deal with the e's as two separate things. So I need a little bit of space. And I'm going to move this. So up here, u plus 7 is equal to 0. And separately, u minus 8 is equal to 0. All right. I would move the terms 7 and 8 first, and then substitute. So, move 7 by a subtraction, u would be equal to negative 7 in this case. And then add 8 here and here. And in this case, u, blue here, is equal to positive 8. All right, now at this point, reverse the substitution. So what is u really standing in place of? E to the x. So I'm going to put e to the x is equal to negative 7. And e to the x is really equal to 8. All right, now here's where some inkling of how the graphs would look would be to your advantage, because you might be immediately suspicious of one of these two. All right. Knowing graphing is handy, right? Here's a graph of an exponential function, the subject of section 6.1, you know. You have a distinct curve that looks something like this, all right? And if the base happens to be an e, as it is in this case, then the y-intercept would be when this is 0 here, all right? So e to the 0 would be 1. All right. 0, 1. All right, and then some secondary point. When you put 1 in here in x, then you get the actual value of e, 2.71, whatever it is. All right, e. All right. So you'd have that curve. All right. Is the y value ever negative? Right? This is a negative 7, right? So if this was y equals e to the x, all right, would the y ever be a negative 7? If it were, it would be off the scale, right? Because there's an asymptote here, right? That's the minimum that anything, that's a boundary that it's never going to reach anyway. This is an asymptote of y equals 0. So be suspicious of this. It's probably a dud. And it's not for anybody's fault, right? It's just sometimes it happens that way. Right? This one is a positive 8. So if you stick in some x, you may get a positive 8 as an answer, whatever it is. All right. Anyhow, we're going to check. Be suspicious of negatives. All right. So, if we were going to continue with this logic, even if you didn't graph something, if you had e to the x is equal to negative 7, what would the strategies tell you to do? They would say, well, if you have an e for a base, then we want an inverse effect, so some kind of cancellation effect. Use natural log here and here, all right? And according to the power rule, this would be up in the front, all right? All right, so this would just be 1. This is x times 1 is just x, all right? So you'd end up with basically this, x to the natural log of -7, right? Again, yeah, that's going to be a problem. If you did it over here, natural log of x and the natural log of 8, the effect is still going to be x times 1. This is going to be x is equal to the natural log of +8. Right? If you enter this into your calculator, you're going to get an error message, all right, for the graphical reason, all right? If you enter this in, you get a nice, well, something of a nice decimal, right? It's going to be 2 and change, you know, 2.0794, whatever it is, okay? Anyhow, when you see a negative attached to a, you know, an exponential equation, all right, be suspicious, all right, because it's probably extraneous, all right. All right. So that one is a dud, not your fault. That is legit. Now let's sort of shift gears here. I've been paying a lot of attention to exponential equations, but the other half of this is where we have logarithms. So, all right, I'm just going to sort of steer you over to this half of the diagram. All right, we'll do a couple of those. How am I out of time? Pretty good. So now we're going to solve the log base 2 of 2 plus log base 2 of the expression 3x minus 5 equals 3. Right? This is definitely an equation because it has an equal sign, and it's a logarithmic equation. Anyhow, remember, this you could try to condense first, right, when it's possible. So these are in fact the same bases, and these are a sum, so you can squeeze these together into one log, all right, according to the product rule, right? Product rule says that if you have a sum of log base 2s, then you could just write them as a product of these arguments, 3x minus 5, and that coincidentally 2 number there. So 2 times 3x minus 5. Okay. It's a little bit too much layer there. Okay. There you go. Let's see. All right, now, if it's in this form, where you have a logarithmic equation, it's just one log here, this is the fun part, all right? You can convert this to an exponential equation, all right? And how so? Because I'm a weirdo. Draw the jelly bean and read the bean counterclockwise. I'm sorry, I'm just self-amused sometimes, and not in the best way. So 2 to the third on one side of equals, right, would be equal to whatever the argument is. So the argument is these two things in tandem. Okay. And then you have an exponential equation, right? Which is not too difficult, right? Just kind of clean it up. 2 times this is 6x, times this is minus 10. This is a regular ordinary number, so it's just 8, right? and solve for x. So you're going to move the 10 in this case over to here via addition, and you get nice numbers that work well. That's 18. So 6x is equal to 18 divided by 6. That means that x is equal to 3. Right. I really should have pointed at this to begin with, but all right. Here's what basically happened. All right. When you get it to the point where you have just a logarithm is equal to a number, as in this case, all right, then why not convert it to, you know, an exponential equation, right? You could apply properties of logarithms if necessary, and also inverses. Anyhow, it ended up being x is equal to 3. No, a couple more of these. All right, here's another one. Say you had 2 times the natural log of x plus 3 is equal to 7. All right, in this case, you have something that is a base e in here, so we might use the inverse if necessary. But we'll isolate first, all right? Move the 3 over here via subtraction. Then 2 times the natural log of x would be equal to, the difference is 4. That works well with dividing by 2. And then you have this natural log of x is equal to just 2, all right? Now, you could convert this to the standard log base e of x and then convert it, and then you'll see what the x is. All right, or you could do it to both sides. Right, if you take apply e to both sides, it would have the same effect. Right, the same effect as if you wrote this as what it really is: log of e is equal to 2. And then drew the jelly bean, all right? And then you have e squared is equal to x, which means x is equal to e squared, and you'd be done, right? But if you apply e to both sides, all right, this is how it would unfold. All right, I'll do it over here. Which is to go, all right, well, for the sake of balancing, if I apply e here, then I'm applying e there, all right? These are, again, inverses, right? And the effect, since you would be raising some base to something that, you know, would be log base e, right? The argument is what would be exposed, right? It would just be x is equal to whatever that is, e squared. Right? Yeah, I'm going to show you just as a reference from properties. This is essentially, it's the inverse property in the second incarnation here. If you put e here, all right, to something that is a logarithm with the same base, then the argument would be exposed. All right, they're inverses. All right, so there's kind of this quasi sort of cancellation effect. Anyhow, you could think about it that way, which is just converting a logarithm to an exponential form. All right, that's what the base would be anyhow. All right, or apply this rule of inverses here. All right, and this is the effect similarly. Okay. All right. 2 more and then we're done. Really gotta clean this. Okay. All right, here's one where graphing would probably be helpful. Suppose you were going to solve something that's just given to you as the natural log of x is equal to 3. All right, if you pulled the trick from earlier, which is to say you're going to try this via graphing, all right, then you have your calculator graph this and graph this and then look for the intersection. That would be the answer, if in fact they do cross. Being that this is a pretty no frills, not too complicated incarnation of a logarithmic equation, all right, you could make some expectations about it, you know, up front. A logarithm like this would curve, being that it's an inverse. If this is what e to the x would normally look like, then the inverse of that, all right, would look like this, right? What would be here would be the coordinates shifted. So if this is 0, 1, then this would be 1, 0, right? And it would be arcing downward like that instead of upward, right? That is this thing in blue here. All right, that's the inverse. Now, simultaneously, you have a positive 3 here. So if you were to put y equals positive 3 in here, they're going to cross, right? That point, whatever it is your calculator would figure out the intersection is, right? That's the solution that they have in common, right? There's some key sequences that would be good to know. All right, if you hit, once you have these things graphed, if you press second and then trace to engage the calc feature, what you'll notice among the options is that there's something that just simply says intersect. In this case, it asks you, you know, kind of redundantly, it's like, is this the first curve, whether it's curvy or not? And then I'll let you go, yeah. And then it says, is this the second one? And then you go, yeah. And I go, you want me to guess where they cross? And you go, yeah. All right, and then it spits out the actual value here. All right, when y is 3, what is the point of intersection here? All right. If instead of doing it graphically, all right, you do it via calculation, again, this is applying e, the inverse, to both sides. And you will get the same answer. So here's the original thing, without the mess in the way. The natural log of x is equal to 3, right? If I apply e here and e here, these being inverses will expose the argument is more or less a cancellation effect. X is equal to e to the third, right? E to the third is, I think, like 20 point something. We'll see. E to the third. 20 and some change here, 20.08. All right, here's the graphic way to do it, which is pretty neat, I think. All right. If you enter natural log of x as the first half, all right, making it its own sort of y equals, and then the right side is y equals 3, it's going to be a horizontal line. You may have to tinker with the zoom a little bit, because you want to see that there's a point of intersection, otherwise it's going to give you an error message. So if you hit graph, all right, you will see at this zoom level that they do in fact cross. Right? Now, to get it to tell you what the point of intersection is, which will be 20 point something, hit second and then calc, trace to get the calc feature. Notice that amongst the choices is intersect, so option 5. And then you go first curve, whether it's curvy or not. Where's the cursor? I can't actually see it at this level. Oh, all right, well, if you move it around. All right, there you see the bug. All right, you go first curve, you go, yeah. All right, and then then it moves up to the line, and you go second curve, even though it's a line, you go, yeah. All right, and then you want me to guess? And you're like, yeah. All right, and there you have it. At y equals 3, it's 20 and change. One more. Right. It's the bells are ringing. Right. say you had natural log on both sides. This would be definitely good to use e then. Natural log of x squared is equal to the natural log of 2x plus 3. Notice in this case, they're both base e really, all right? So if they're both base e really, again, nobody ever bothers to write this, log of base e, all right? Log of base e. But if it makes it more obvious to go, well, they're the same, aside from the ln and the ln, these would have to be 1 to 1, all right? They have the same bases. They're the same logs on opposite sides. So you could take advantage of the 1-to-1 incarnation of these techniques for logarithms per se. That means that you just have to pay attention to the arguments only, all right? And therefore your equation is x squared is equal to 2x plus 3, and it's quadratic. So manipulate it, bring these things over equals one at a time. Subtract, subtract, and you end up with x squared minus 2x minus 3 would be equal to 0, which is something that you can for sure factor. If it's x squared, it's probably going to be an x in here and an x in here, and if it's 3, it's going to be a 3 and a 1. And you want them to be a negative when multiplied, so one of each sign, all right? If you want the outcome to be negative when you add potentially subtract them, and you want them to subtract, you attach the negative to the larger magnitude, and then you have that. So each one of these, you're going to apply the zero product rule. There's no substitution in this case. You have x plus 1 is equal to 0, and x minus 3 is equal to 0. In this case, you subtract 1, x is equal to negative 1. And in this case, you add 3. So you get x is equal to positive 3. Now what you should do, again, to check for extraneous solutions is substitute either of these back into the original equation and make sure that they balance. Right? I would always be suspicious of negatives. So, but because it's a negative that's going to be squared, ultimately, it shouldn't be a problem. Right? If you did, to be a good sport, check both of them. This would be, in one case, the natural log of 1, which is a legit number. If you put a negative 1 here, 1 squared is still 1. If you put a 1 here, it's 2 times 1 will be natural log of 5. That's weird, but okay. Let's see. All right. One of these is going to be funny. Oh, wait, because it's negative. Sorry. Yeah. 2 times negative 1 is negative 2. So, yes, you will get a 1 here and a 1 here. All right, so positive 1 is for sure one of the parts of the graph. So whatever decimal you get here, that's going to be fine. All right. If you stuck in positive 3, this would be the natural log of 9 on one side. And this would be 6 plus 3 would also be 9, natural log. So it balances. They're both cool. Okay. All right. That's it for now. Thank you guys for sticking with me. This video is for Thursday. I will see you again on Monday. All right. I anticipate probably have homework from section 6.5 and 6.6. Okay? All right. See you later. Be careful out there.